Once the design is complete, deployment documentation is generated and provided to the installer. This is a list of all devices, physical locations, and configuration specification. Based on this, the installer configures, deploys, and verifies the design on site. Post-deployment, the user can now use the SCUBA toolchain to commission the system. The Coordination Scheme Editor enables the extension of the existing device and system functionality by supporting the design and inclusion of soft devices, sensors or actuators, and scenarios. Using a browser, the user can open the Coordination Scheme Editor and select a building of interest from the list of available buildings, and as a result the corresponding layout and available devices are shown. The user selects soft device and new soft sensor. A list of available sensor types is displayed and the sensor interval and operator settings need to be defined. The user selects the sensor types of interest for inclusion in the definition of the new soft sensor. These are then automatically listed in the order of selection in the sensor list box. The interval range over which the device is to operate must be set. This can be defined between limits A and B or can be selected based on predefined intervals. These actions are repeated for all selected sensors, with the interval ranges for each sensor being shown in the interval list box. Having the sensors defined, the next step is to logically link the list of sensors using a mathematical operator, which is selected from the operator list box. The user can define an operator or select an operator from a list. The user can now save the new soft sensor, which automatically generates the required rules for deployment within the SCUBA coordination middleware. The soft sensor can be applied to rooms where the physical sensors are available. For example, if a comfort soft sensor is defined based on temperature, luminosity and humidity physical sensors, then this comfort sensor can only be applied to rooms that have those physical sensors available. If they are not available, then the selection of the comfort sensor for that space has no effect. Once verified, the soft sensor becomes active within the live system. The user can also use the Coordination Scheme Editor to define building-specific scenarios based on the sensing and actuation capabilities available within the building systems. The user follows a similar procedure as used in the definition of the soft sensor. Consider the definition of a new lighting control scenario, for example. Here the objective is to automatically switch on the lights once the ambient light levels fall below a specific threshold. For this scenario, the luminosity sensor is selected and the user defines a light level threshold of 350 lux. The user then also selects the actuator, which will switch on the lights when the condition is met. When the scenario definition is complete, it is now available for application to areas of interest within the building. After the building systems have been deployed and commissioned, it is essential to ensure they operate as designed. The SCUBA toolchain facilitates this. The toolchain component, known as the Strategy Manager, enables continuous commissioning by closing the loop between the system operation and the design in order to adapt or evaluate the impact of a change on the system operation. To enable the data mining and system analysis, live data needs to be input and stored within the toolchain. This is facilitated by the Strategy Manager that allows for the definition of a data model that is mapped to the SCUBA data warehousing approach. This is currently achieved by implementing several Strategy Manager API interfaces and deploying them within the Eclipse Virgo container as OSGI services. The implementations are responsible for the declaration of data, types and connections that are stored, the transformation step of the extract, transform, load paradigm of the data warehousing approach employed by the Strategy Manager. The SCUBA Strategy Manager API defines both the input for the transformation and the end result of the transformation. The transformation typically uses the BASON to add metadata, such as the location of a device, to the measurements that come from the SCUBA middleware. With the data storage defined, the second step is to develop data monitors. This is achieved by creating a new class that implements two Strategy Manager interfaces. Firstly, Monitor, and secondly, Fact Listener. The former implements the monitoring functionality, and the latter gives access to the semi-real-time data stream that flows through the Strategy Manager. The user can implement detection logic using this data within the Monitor class. Examples that are currently implemented include monitoring of the energy usage of the lighting system, monitoring of the functionality of the lighting system, such as is the light switched on at night when nobody's in the office, and lastly the self-monitoring of the Strategy Manager, such as memory usage and performance of the data storage. As mentioned previously, the Strategy Manager facilitates scenario adaptation. So the third step shows the human-in-the-loop approach to adaptation taken by the Strategy Manager. The data monitors of the previous step are in one of three states inspired by traffic signs: green, yellow or red. These monitor states are visualized by the Strategy Manager GUI. Furthermore, the GUI shows time series of the data that underlies the visual state of the monitor. In the case of the control chart for the energy consumption of the lighting system, the user can zoom into the data that underlies a point in the control chart. The user can then interpret the situation and take action if required. You can also see here an example of how the monitors are used to self-monitor Strategy Manager. We can zoom in to the storage size, which monitors the amount of disk space needed for storage of the historical data set.